Hey Billy, this is Kevin Shryock giving you the video response for the homework question you submitted. So you were asking about this physics problem. At the bowling alley, a ball feeder must exert a force to push a bowling ball up a 1 meter long ramp. The ramp leads the ball to a chute 0.5 meters above the base of the ramp. Approximately how big force how big of a force, there we go, must be exerted on the 5 kilogram bowling ball by the pushing mechanism to push the ball steadily from the bottom of the top of the ramp, from the bottom to the top of the ramp. Wow, that's a lot of stuff. So what I like to do always when I am working with a physics problem is follow a very disciplined method. I like to start always with drawing a picture. This already provides me with a picture, but I want to see what else I can add to it. So if I was going to add things here, there's a lot of information in the problem. It says that I'm talking about forces, right? So how big of a force must be exerted on this ball? So here's the force that's being drawn. What else is affecting this ball in terms of force? Well, I've got a force of weight that is always coming down, right? A force due to gravity. I'm going to call this force weight, or maybe I'll just refer to it as W. What else is happening to this ball? Well, I've got a normal force right here. Let's call this N. The normal force is whenever two bodies are in contact, there's going to be a normal force. What else do I have? Well, that's pretty much good for the picture. Let's move on to listing out the variables. What else does it tell us? It says that I have a mass. The mass is going to be a 5 kilogram ball. It says that I have a distance of 0.5 meters. That's already drawn in here. That could maybe come in use. I'm gonna write this maybe as D. So D is equal to 0.5 meters. What else does it tell us? It tells us that I have a length that it's going across. Maybe this is the displacement that it's going. Okay, so we'll write that as a delta x equals 1.0 meters. That's about it. So what can we work with? Well, we know that this is talking about a force that is moving the ball up at a steady velocity. So the ball steadily moves from the bottom to the top. So that tells us that there's not going to be any acceleration, right? So if the ball is moving steadily, that means the velocity is always the same. That means that there must not be a change in velocity, and change in velocity is acceleration. So there must not be any acceleration. Let's write that over here. So acceleration, I'm going to call that acceleration net, is equal to 0. So let's take, whenever we have a free body diagram, it's a good idea to start with our laws for forces. So we've got, right, Newton's second law, which is the sum of forces, is equal to the mass times the acceleration net, which is equal to the force net. And what to talk about? Well, I've got a bunch of different forces here, and there's a bunch of different angles. I've got N that I don't know. I've got the force that I don't know. I've got force weight, which I could calculate, but I currently don't know. And the way that it's oriented right now, if I was going to break this down into its x and its y, I was going to say the sum of forces in the x is equal to the mass times the acceleration in the x, and the sum of the forces in the y was equal to the mass times the acceleration in the y. I'm going to have to include everything, and I don't really want to because I'm a simple guy and I like to do simple math. So let's see if maybe we can turn this entire free body diagram to the side, and that might make our math a little bit easier. Well, there's nothing wrong with me redrawing this free body diagram as saying, let's have the normal force pointing up. Let's have the force of weight, which was pulling straight down. Let's now tilt that a little bit. Let me scoot this so we can see both. There we go. Let's now tilt that a little bit. So this is now our force weight. And let's make the force being applied go straight across. This works a little bit better because now if I was going to do it in the x and the y, the x-axis is only going to have my w and my f, a component of the w and the f. It's going to ignore the N force. And then in the y, I'm just going to have the normal and the weight. And that's going to ignore the F force, the applied force. I like this better because it's going to make my math have less variables in each of these equations. And again, like I said, I'm a simple guy and I like to do simple math. So let's see what else we can do for here. Well, this is often an angle, and I should be able to describe what that angle is. I don't really know what the angle is right now, so I'm just going to call this angle theta. Alright, let's make that maybe a smaller pen stroke so that that actually comes out as a nice theta. There we go. Let's make this theta. I like it. Okay, moving down with the rest of our math. If we are going to break down the sum of forces in the x using our new free body diagram, well, the sum of forces in the x, I've got a positive F force. I've got a positive F force. I've got a negative weight component, and my component is going to be the opposite of that angle theta. So the opposite of that angle theta is going to be our sine component, so sine theta. Now, what about the acceleration? What do I know about acceleration? Well, we said originally that the acceleration net is going to be 0, which means the acceleration in the x has to be 0 and the acceleration in the y has to be 0. So I can actually just take all of this and turn it into 0. Great, let's write that one for the other one, because now I've got, let me go back to our diagram. Over here I've got the normal force is moving up in the y. I've got a component of the weight that is going down. This time it's going to be my cosine, because I'm looking at this component that is directly adjacent to my angle theta, equals 0. Alright, so let's keep breaking this one down. Well, before I go too far, I want to make sure that I can find out what this theta is. I don't think that we're going to be able to solve it without it, because it looks like all I'm trying to figure out is the force. The force is over here to the left. Weight is easy to calculate. It all equals 0, but I don't know what this theta force is. Okay, how can I figure out what the theta force is? I'm going to go over here and draw a diagram that shows how the angle of a plane, the surface, directly affects the angle that that weight is. This is going to bring back some geometry, so if you want to skip ahead and just sort of accept the concept, you're welcome to do that, but I always like to have a bunch of different reminders when it comes to a test. So let's say that this was our weight force, which goes straight down. This here on the inside is our angle theta, right? Well, this I can draw kind of similarly using triangles. Is the same as if I drew that. You see how this shape up inside of the box and the big shape of the the ramp at the bottom is just about the same, and this is going to be a 90-degree angle because it's going straight down through the box. This is a 90-degree angle with the ground because the weight goes straight down. Well, if this up here is my theta, then this here must be 90 minus theta. In order to make a full triangle, I have to add up to 180 degrees. This is a 90-degree angle. This is a theta angle. This must be the remainder to get up to 180, which is 90 minus theta. Similar triangles, opposite and adjacent angles within triangles, or two lines, tells me that this has to be the same angle. And if this is my 90 minus theta, and this is 90, this guy here must be theta. So what are we kind of proving by drawing this? In a situation where I have a box and I'm given an angle or any type of description about the ramp, I know that as I tilt my free body diagram, I'm essentially creating that angle with the weight force. So if we go back over here, this angle theta is being created by the height that the ball is traveling and the hypotenuse that it's traveling along. This is my theta value within the picture. Okay, so what can I do? Well, to calculate theta, I can do some side work over here, and I could say that theta is equal to, well, it gives me the opposite side, and it gives me the hypotenuse side, so I could say sine of theta is equal to the opposite, which would be my 0.5 meters, over my hypotenuse. My hypotenuse was this 1 meter length. So theta is equal to the inverse sine of 0.5 over 1. Which, if you remember your unit circle, will come out pretty nicely. If you don't, that's okay. This just turns into a 30-degree angle. You can type that into your calculator, right? Inverse sine of 0.5 over 1. Okay, let's go back to where we were originally in the problem. Now it seems like I know just about everything. The force, I can solve for the force. The force is equal to, well, moving the W to the other side gets me W sine theta. I can plug in what I know, which is that W is equal to the mass times the gravitational acceleration constant times sine of theta. And now I can plug in everything I know because I know mass, I know gravity because that's a given, and theta, oh yeah, theta I calculated down here. So I could say 5 kilogram object times the gravitational constant of 9.8 meters per second squared times the sine of the angle 30 will get me my force. And if I type all that in, I should get, let's see, 5 times 9.8 times the sine of 30 gets me 24.5, and this is a force, so I'm going to measure this as newtons. Good, let's go back up and make sure that we've got the answer it wanted. Approximately how big of a force must be exerted on the ball by pushing the mechanism, or by the pushing mechanism, to push the ball steadily from the bottom to the top of the ramp. So if we recap everything we did, we first started off with saying we were going to draw the picture, and the picture was talking about forces. The best way to draw forces was to go over here and to do our free body diagrams. So our free body diagram was both here and here. Our free body diagram led us into our forces equation because this always holds true. And then as we were trying to solve it, we decided to make our lives easier. Let's flip the free body diagram. Let's figure out what all the components are that go into our equation, our W, our theta, and then we solved straight down just using the math. So this is the final answer we're going to give into our teacher. Maybe on a test, since it says approximately, this is going to be given the answer of saying 25 newtons, and that'd be a fair response too, because it's approximately 25 newtons. All right, thanks so much, and I hope you enjoy.